everybody, I am Chebyshev, and in this lecture I am going to explain the concept of center, variability and shape, calculate and interpret common measures of center, calculate and interpret common measures of variability, apply Chebyshev's theorem, apply the empirical rule and recognize outliers, transform a data set into standardized values, calculate and interpret a correlation coefficient and covariance. So let's start by defining the center, variability and shape. In the last lecture we studied how can we describe any data set visually. In this lecture we will focus about describing the data set using numerical measures. To describe any data in a numerical characteristic, it's very important to realize what is the center for this data, what is considered the data point, the middle of this data, and how all the observations in the data set are dispersed around this middle point, and what is the shape of the distribution of the data set. Before we graphed the data set, the frequency of the observations using histogram. So the histogram provide us with a description or to know the frequency of each value inside the data set. So what is the shape depends on how the data are distributed around the values and around the mean, and how they are dispersed. Where is the concentration of the observations? Are they around the mean? Are they far away from the mean? Are they at the left, concentrated at the left of the mean, or at the right of the mean? So let's start to explain the variables or the measures of center, variability and shape. So for example, if we have this data set that's inserted inside the table, which is measuring the number of defects inside each brand. So if we sorted the number of defects from the smallest to the largest, we'd realize that the smallest number is 83 for Porsche, and the largest number of defects is 170 for Land Rover. Of course, as we sorted our data, we would consider that there is the left, which is started with 83, and the right, the right of the data which ends at 170, and most or the center of the data which is between 111 for Audi and 121 for Subaru. So for example, if we are considering the distribution of this data, we would say that almost all the data would be concentrated here in the area between 111 and 121, and the maximum number is 170 and the minimum is 83. So we need to measure and to give exact numbers for where is the middle of our data. Our data is concentrated in this area. What's the shape of the data? Is it like this? It's symmetric, where the positive area almost equals to the negative area, or is it skewed to the left or skewed to the right? So we will start with considering the numerical measurement. If we started to again describe the data visually, we can see that most of the data are concentrated in this area, and we have here 170 as an outlier because it's really far away from all the concentration of the area. This, of course, indicates that it's not symmetric. Why is that? Because we have here some observations. We don't have here any observation. We have this as unusual. It's to some degree it's far from the concentration, and this is considered as outlier because it's really too far from the concentration of the data. So if we look at this histogram, we can say that the concentration of the data, again, as the dot graph supposed or assumed or showed, that most of the concentration of the data is at the left, and we have here a long tail at the right, and we found that at 170 it's an outlier value of our observation. So this frequency or this histogram shows us the shape of our data. So let's start with the mean. The mean or the average of the values included in the data set is considered as the center. It's one of the most famous measures of the center of any data set. To find the center of the data set, we simply add the value of all observations and divide this addition by the total number of the observations. So here, if we are considering the population mean, which is called mu, it's the summation of all observations included in the population divided by the total number in capital of the observations inside this population. Of course, we said before that it's very difficult to estimate the value for all the individuals included in the population, especially if we have infinite population. So in this case, we try to estimate to find a statistic for this parameter, and this statistic is called a sample mean. In this case we call it x bar, not mu. Mu refers to the population mean, but x bar refers to the sample mean, and x bar in this case equals again the summation of the values of all the observations included in the sample divided by n small, or the number of individuals inside the sample. The most important characteristic of the mean is that it's called a balancing point, because it has the property that the distance, the summation of the difference between any point above the mean and the summation or the difference of any point above the mean, this will yield the value of 0. So if we summed the difference between 40 and 65 and this difference plus the difference between 70, 65, 75 and 65, 80 and 65, and so on, if we sum all these differences, we will get the value of 0. This is because the mean, it gives us an estimate or evaluates the middle point at our data set. So let's start with a very simple example to calculate the mean for grade of 4 students. We have here student names and their grades. To find the mean or the average of the student grades, we simply add 60 plus 70 plus 80 plus 70 again. We add all the values of all the observations included in our sample, and we divide this by the total number of observations. We have here only 4 students, so we add them. They are added to 280. We divide this by 4 to get the mean of 70 grades. So the average grade of all students included in this class is 70. The second measure of centrality is the median. Median refers to the midpoint when we sort our sample or our data. After sorting the data from smallest to largest, we try to find the midpoint, or the point that is dividing our data set into 50% upper than this midpoint and 50% lower than this midpoint. So the median is called the 50th percentile, or the midpoint of the ordered sample data. So M separates the upper 50% of the data set and the lower 50% of the data set. Again, to calculate the median, if we have this example of student grades again, so the first step we need to do is to sort the data. We must at the beginning, to find the median, we must sort the data. So here it's not sorted, then we are going to sort the grade from the lower to the largest. We have here 60, 70, 70, 80 and 85. So the median is the point that splits the data into upper 50% and lower 50%. So here the midpoint is the 70. So in this case the median or the midpoint equals to 70. This example refers to finding the median in the case if we have number of observations is odd. So after dividing, we have here 5 observations. If we divide 5 by 2 in order to divide our data into 2 halves, we will find the result is 2.5. So after 2 observations, we find here the value at the middle, then we have other 2 observations. This is too simple if we have the number of observations as odd number. But if the number of observations is even, number of observations is even, in this case the midpoint is exactly here. We have the number of observations is 4 divided by 2, so it's 2. So in this case we have to add the second and the third observation and divide their value by 2. So here the second observation is 70, the third observation is 80. We have to add them and divide them by 2. Of course 70 plus 80 equals 150 divided by 2 gives us 75. So this is the value of the midpoint inside this data set. The third measure of centrality or the midpoint is called the mode. Mode is the most frequently occurring data value. So if we look to this graph, we would realize that the most frequent, the most occurring value are here when the observations value equals 10, and here when the observations value equal 16. So the most frequent value here is at the points 10 and 16. Sometimes we may not have a multiple modes like this, or we may have no mode at all if the data has no frequencies where each values are represented by only, or the repetition for the value happens only once. In this case the mode equals 0. So to calculate the mode again, it's the most frequent value. If we look at these values, we'll find that 60 is repeated only one time in the data set, 70 repeated twice, and 80 also appears only one time. So in this case the most frequent value, the most repeated or occurring value is 70. In this case the value of the mode is 70. Also there is a measure of the center of the data. This measure is called the mid-range. In mid-range, we simply take the minimum value appeared in the data set, add it to the maximum value, and divide this by 2. So for example, in the example of defects, we had the least value was 83 plus 170. It was the maximum value. We add these two values and divide them by 2. So in this case, we would find the mid-range, and we will consider this as a measure for the center of the data set. The mid-range, the problem with the mid-range is that it's very sensitive to extreme values. How is that? We said in the graph, we saw that 170 is an outlier. It's really far away, appeared far away from the concentration of all the values. So we can't say that this mid-range will give us the value that represents the real midpoint or the real middle of the distribution or of the observations. So mid-range is very sensitive to extreme values or to the outliers included in the data. To compare the four measures of centrality, we can see, or we have here two tables, table 1 and table 2. In table 1 we have these different grades. So to calculate the mean, we simply add these 5 numbers together and divide them by 5. To find the median, we have to sort the grades from the lower to the largest value, the smallest to the greatest. Then we find here it's 5 observations, so the point at the middle or the midpoint is gives us the value of the median, which is 70 again. There is no repetition inside our data, so in this case the mod equals 0. The mid-range equals 70. If we add 50 plus 90, it's 140. Divide them by 2 gives us 70. To compare the same measurements with a slight difference in the data, where the student X gets 45 instead of 50 and student V gets 95 instead of 90, we would find that the mean is totally changed from 70 to 61.8 and the median remains as it is. We have the mod equals 0 and the mid-range equals 70. The most robust measure for the center or the middle of the data set is the median. Why is that? Because it is not affected by the values at the extreme ends of the data set. We just find here if the data is shifted from 50 to 45 and from 90 to 95, the mean is totally affected by the extreme values at the upper and the lower ends of the data set. Of course, mod is considered one of the weakest measures of centrality because it doesn't tell us about anything inside this data. If no frequency or no observation is repeated, we'll get the value of 0, which will give us no information about the data set. Mid-range, we said its main problem is that it's totally affected by the extreme values. So if we'd have here 100 for example, and here 20, in this case we'll find the mid-range will be 20 plus 100 divided by 2 equals 60. It's totally different from the 70 we get here. Even if the numbers changed to 100, the maximum and the minimum from 45 to 20, we find that the median is still the same value. It's 70. So this is why we consider the median is the most robust measure of the centrality inside of all the four measures. So after calculating the measure of centrality using different measures, mode, median, mean, and the mid-range, we can see how can we benefit from these numbers to understand the shape of any data set. So if we compare the mean, the value of the mean, the median, and the mode, and we can see here the case where the right hand side or the right distribution of the data almost equals the left distribution of the data is called symmetric or bell shape, as it looks like the bell. Okay, so in this case we'd find that the mean equals the median equal the mode. The three of the measures must equal to each other. So if we have calculated these measures and we find that the mean equals the median equal, for example, the mode, in this case would say that without knowing or drawing the distribution of the whole data, the histogram, we can say that the data is symmetric, and we call it is normally distributed. It's normally distributed. Okay. The two other cases, if all the data is almost concentrated at the right with a really long tail, this is called the tail of the data, long tail at the left, we call it skewed left. The data is skewed to the left. And to have indication about this shape, always the mean is less than the median. The mean is less than the median. The other type is if the data is skewed right. So in this case, most of the data concentration is at the left with a long tail at the right. In this case, we call it, we say that it's skewed to the right. So the direction of the tail tell us about the skewness of the distribution. If the tail is long at the right, it's skewed to the right. If the tail is long at the left, it's skewed at the left. For the skewed right shape, the mean is larger than the median. So the mean in this case is greater than the median. But here the mean less than the median. In this case, we say that the shape of the data is skewed at the left, and here the data is skewed to the right. And of course, the middle case refers to the normal distribution, or we say the data set is normally distributed. In this case, the three measures, and we are most important ones, the mean and the median, and also the mode will be equal to each other. So after referring to the center of the data set, we need to know the measure of variability. By variability here, we need to know how spread of data points. So here the variation or the spread of the data give us insights about the shape of the distribution. If all the data is concentrated around their center, or there is a really high variability that the curve looks smooth like this. In this case, we have here the observations are very far away from their center. So first measure of variation is the range. In the range, we just subtract the maximum value minus the minimum value of the observation. So if we want to calculate the range for the first defect data set, in this case we just will subtract the maximum, which is 170, and the minimum value, which is 83. Another and the most reliable measure of variation is called the variance and the standard deviation. The standard deviation is just the square root of the variance, so both of them are considered as following the same rule. The population variance is called sigma square. It's the summation of the squared difference between x, the individual observations, and the mean of the population. In this case, it's called mu. Remember that we said if we calculate the summation of the difference between observations and their means, this summation will give us a value of 0. So this is why, this is because the negative values will cancel the positive values around the mean. Later we'll see an example that depicts this relationship numerically. So to avoid this problem of getting the 0, we will square the difference. In this case, the result of any difference between xi and mu, all the differences will hold the positive value, and we get here some number. This number will be divided by the total number of observations inside this population, which would give us the value of the sigma square, or the variance of the population. Of course, as we've said, it's very difficult to calculate these measures for the population. This is why we try to estimate these measurements using the sample statistics, and we call it S square. Refers to the variance of the sample, and we sum to find that we sum again the difference between the observations and the sample mean. Of course, we square it because of the same reason, because the difference between the sample observations and their mean will equal to 0, because the negative values equal to the values with the positive numbers. To avoid this problem again, we put the power 2. We get the square of the difference between the values from their mean, and we divide them by n minus 1. N refers to the total number of the observations inside the sample. We here subtract 1. 1 is called the degrees of freedom. This is why, because we used our data to calculate the mean of the sample. So we have some constraint here about the data, about the mean of the data. In this case, we will subtract -1. So the general rule, you always, if we are going to calculate the variance for the sample, we divide by the total number of observations included in this sample, and we subtract 1 from the number of the observations. Of course, as I've said, the standard deviation is just the square root of the sigma in case of if we are calculating the variance of the population, and it's the square root of s if we are calculating the standard deviation of the sample. It's very important to get the standard deviation if we are putting some conclusion. This is because after getting the square root, we eliminate the squared effect. So in this case, we'd have the standard deviation with the same units as the observations included in the sample. So for example, if xi measures the kilogram and we are differentiating them from their mean and square them, of course it will be in another measurement or another unit. Getting the square root of this will reveal at the end the same unit of the observations included inside the data set. We have here what's called coefficient of variation, which is very useful if we want to compare two data sets. We have two data sets, okay, data set 1 and data set 2, and we have an estimate for the standard deviation for data set 1 and another estimate for the standard deviation of data set 2. If we want to calculate the two data sets, we must unify the way of the two measures of variation in these data sets. So if, for example, the first data set is measured using different units than the other data set, or this data set measures some observations that are different from the other data set, in this case we want to make both of them to be as if we want to eliminate all the differences to make the comparison more easier. So other example why we would do the coefficient of variation, if two data sets have two different mean, how can we compare the dispersion in two different data sets with two different means? So in order to avoid all these differences and to obtain a unit-free measure of dispersion, we calculate the coefficient of variation CV. In this case, it's equal to the standard deviation divided by the mean of the sample, and of course as it's a ratio or a percentage, we multiply it by 100%. So after doing this, we are dividing the standard deviation of the data set with its mean. In this case, we would have two coefficients of variations. Two of them are unit-free measures of dispersion. In this case, we can compare the two data sets. Also, it's very important to understand the Chebyshev's theorem. For each data set, we found that there is mu or x bar, and for the dispersion measure we have sigma or s. We can standardize the data and mean by standardize the data if we have xi refers to the observations inside our data. So xi refers to the grade of the first student, and this is the grade of the second, and so on. If we wanted to obtain a data set, we transform this data set to a new data set where the mean equals 0 and the standard deviation equals 1. In this case, we call it, or this process, standardize our data. So to obtain the data like this, to do this shift, we mean to obtain what is called z-score, and z-score equals xi negative x bar divided by s. So we have to subtract the mean from each data value and divide it by the standard deviation. We have to apply this to all the xi's. In this case, the new data set obtained is called a standardized data set. If we calculate the mean for this data set, it will be equal to 0 as it's already subtracted from all the observations. And if we calculate the standard deviation of this data set, the standard deviation in this case equals to 1. So according to Chebyshev's theorem, for k equals 2 standard deviations, would find that around 75% of our data are included around the mean, and at least will lie here without the mean plus or negative 2 standard deviations. For k equals 3, the standard deviations here, so about 88.9% of the data are included or are lied between the value of the mean plus or negative 3 standard deviations. For the empirical rule, the empirical rule say that the normal distribution is symmetric. As we saw before, it's symmetric, it's bell-shaped, and is also known as a bell-shaped curve. The empirical rule states that for the data from a normal distribution, we expect an interval mu plus or negative k sigma to contain a known percentage of data for If k equals 1, around 68% of the data lie within one standard deviation away from the mean. So here is the mean. If the data is normally distributed, there is here it's mu plus sigma, and here it's mu negative sigma. So in this area where between mu negative 1 sigma and the area between mu plus 1 sigma, in this case there is about 68% of our data observations in this lie in this area. For k equals 2, about 95% will lie in the area m plus or negative 2 sigma, and if k equals 3, about all the data is included within 3 sigma. The following figure will illustrate more this idea. So here is the mu, here is the mean of the data. If we have an interval between mu negative 1 sigma and mu plus 1 sigma, the area included under this curve will contain about 68.26% of all the observations will be concentrated in this area under the curve. If we enlarge more our interval, if mu minus 2 sigma to mu plus 2 sigma, so we have all this interval, so all this area under the curve will contain about 95% of all the observations inside the data set, and the third interval, the larger interval, that is mu negative 3 sigma to mu plus 3 sigma, will contain about 99.7 or 100% of the observations under the curve. I think it does make sense if we think about all the observations. So here 3 sigmas plus the mean or minus the mean, if we are away from the mean by 3 sigma to the right or to the left, it will contain the whole curve that represents the all observations in the data set, and in this case it will contain around 100% of the observations. So it requires only 3 sigma plus or negative mu to include all the observations under the curve. So again, to standardize our data to obtain what is called z-score, we follow this minimize standardization formula where zi will equal to xi. Xi refers to the individual observations inside the data set. Negative mu, the mean, divided by sigma. Of course, this is the case if we want to standardize the data included in the population. Again, it's very hard to deal with the population, so we deal with the sample. In this case, to standardize, to obtain our z-scored data elements, we just do the same. We subtract from individual observations the x bar or the mean of the sample, and we divide this by S, which refers to the standard deviation of the sample. Of course, if Zi equals negative, it's a value at the left of the mean. So here, if this is the mean x bar, if we subtract xi negative x bar and we get negative value, so this means that xi is greater than x bar. In this case, it's some value here at the left. But if the difference between xi and x bar gives us a positive value, so this means that the value is at the right to the mean. We have said, we saw before that in the example of the defects of the cars and brands, we saw that we have a value of 170, and it was here one only frequency for this, and most of the data were concentrated in this area, and we have a right skewed distribution, or the data were skewed to the right as the tail is long at the right. We had only one value, which is 170. So how can we know is 170 is really an outlier or not? So we can check this by considering the absolute value of Z score. So if the absolute value of the Z score is greater than 2, in this case we call the observation an unusual one, and if the Z score is greater than 3, we call this observation an outlier. Of course, here it's mu plus 3 sigma. Zi is a standardized or a Z score. So in this case, we have here mu for Zi equals 0 and sigma equals 1. So this is why we consider the value of 3, and here also it's 0 plus 2 multiplied by 1, which is 2. So this is why we consider if Zi, the standardized value, or the Z score is greater than 2, in this case we call the observation unusual, and the Zi, if the absolute value of the Zi is greater than 3, we call this observation an outlier. So to check any observation inside the distribution, and we want to know is it unusual or not, or is it an outlier or not, we have to check these two rules by find the Z score for this value. The Z score for this value will equal to 170 negative the x bar of the distribution divided by the standard deviation. After obtaining this Z score or the standardized value, we would check if the absolute value of Zi is greater than 2. In this case, it's unusual, and if the Z score is greater than 3, in this case it's called an outlier. So At the end, we will consider how can we calculate the variance and standard deviation. We have also a very important measures of variability, which is called the covariance of two random variables. So in a scatter plot, when we have a relationship between two variables x and y, and we have scatter of points like this, can we say that there is a positive relationship between x and y, or a negative relationship, or there is no relationship at all? To check if there is a relationship and what is the direction, is it a positive relationship when x increases, y increases too, or it's a negative relationship if x decrease or increase, y would decrease? And how strong this relationship? We calculate two very important indicators called the correlation and the covariance. So to start with the covariance of two random variables x and y, denoted by sigma xy, measured the degree to which the values change together. So here for the population covariance, in the variance sigma square, we add the difference between the values and their means and divide them by the number of observations. So in the covariance, as it's the relationship between two variables, we can consider here the variance as it's xi minus itself twice, okay, divided by n capital, as this square refers to. But for the covariance, we would consider the difference between the first variable, the difference between the observations of the first variable from their mean, and the difference between the second variable to their mean divided by n. So it's almost the same definition, but here as it measures the relationship between two variables, instead of getting the difference between the same variable and its mean, we would consider the difference between the first variable to its mean multiplied by the difference between the second variable and its mean. Of course, this is if we are calculating sigma xy, or the covariance, the population covariance. Again, it's very hard to calculate this measure, so we estimate the covariance Sxy for the sample, and in this case we measure the difference between the observations and their sample mean for the first variable, and the difference between the observations and their mean for the second variable, and again it's divided by n-1 for the same reason we did when calculating the variance for the sample. So for the after calculating the covariance, we can get a value of the correlation between the two variables. In the correlation coefficient, we also eliminate all the differences between the variables, and it's considered as a standardized value of the covariance, which will be in between the range of -1 and +1. So the correlation coefficient for the population or rho equals sigma xy divided by sigma x and multiplied by sigma y for the sample correlation coefficient, which is small r, equals the sample, the covariance of the sample sxy divided by the standard deviation of x multiplied by s of y. So there is an easier way to calculate the sample correlation coefficient. Instead of using this formula, we can use this formula, which is the multiplication of the difference between the variable and its mean in the two variables divided by the squared difference between the sample for each variable. This figure shows how can we interpret the correlation coefficients. So if the data is scattered like this or like this, we would say that, and the r of course in these two cases would equal or approach the zero, we would say that there is no correlation between the two variables. If we want to represent this data by a straight line that passes through these points, we would see that this straight line is or has a slope of zero slope. So it's a constant line. This is why you would say that there is no relationship between x and y. As if there is no relationship, we would say the two variables are not correlated. If the variable is around, or the correlation is estimated around 0.5, if it's positive 0.5, we would say that there is a positive correlation between x and y. As x increases, y increases too. So there is a positive correlation between the x and y. Also, in the other direction, if there is a relationship between x and y, and this correlation is estimated to be around -0.5, in this case we say there is a negative correlation between x and y. As we can see, when x increases, y decreases. As x increases, y decreases. Also, if there is a really positive, strong correlation, the value of the estimated correlation will be near 1, approaches 1, or will be greater than 0.5, much greater than 0.5. It's near to 1, like this, it's 0.90. In this case, we'd say there is strong correlation between x and y, and as we can see, the data points are really not dispersed, and all of them are concentrated about an imaginary straight line representing the data. In the opposite direction, if there is a strong negative relationship between x and y, the correlation coefficient will be estimated to be near to -1, or approaches -1. Let's take a numerical example to illustrate all what we have talked about, have taken about all the mean and the different dispersion measures. So if, for example, we have a data set that contains two variables x and y. The data set was collected in the purpose to check is there a relationship between the years of experience and the salary of employees. So the big question is there a correlation between the salary paid to employees and the number of years of experience? To check this, of course, or to answer this, we need to find the correlation coefficient. To reach this end, we must at the beginning calculate the mean of the value x and the mean of the variable x and the mean of the variable y. So to calculate the mean, it's simply the total number, the addition of the values included in x divided by the number of observations. We have here 5 observations, so in this case the mean is 7,250 divided by 5. We get 1,450. This is the mean salary of all the employees in the company, and the average or the mean number of years is 12. It's of course obtained by dividing the total of the years of experience of the 5 employees. We divide them by number 5. It's 60 by 5. In this case we obtain 12. So the formula to get here for the covariance, again it's summation of xi negative x bar multiplied by yi negative y bar divided by n negative 1. So we need to calculate xi negative x bar. We did this in this column, and we multiplied, we get xi minus x bar, then we get yi negative y bar. This is simply the difference between the salary and the x bar. So to get this number, we subtracted 1,000 negative 145 to get negative 45. This observation is at the left to the mean, or it's smaller than the mean. We continue with each observation. 1,500 negative 1,450, we get positive 50, and negative 500, 550, 350. If we add all these numbers, if we add these numbers together, we get 0. This is because the negative numbers are added to negative 950 and the positive numbers are added to 950. This is why we say that the mean is the balancing point, because all the sum of all the difference before the mean and the difference of the observations to the mean at the right hand side and at the left hand side, both of them would give us 0. So this is why the mean is the balancing point inside our data set. We will do the same for the difference between the IY and I bar and Y bar, and also to get the difference between the YI and Y bar. After getting the difference, we would multiply each difference with this. So we will multiply the negative 450 by 3 to get negative 1350. Then for the second observation, we multiply 50 by 0. In this case, we get 0. Then we multiply negative 500 by negative 1 to get 500. 550 by 0 to get 0. And at the end, 350 by negative 2 to get negative 700. We find the total. This is the total of the multiplication of the two terms. We find the total, which is negative 1550. Divide this total by n negative 1. We have here n or 5 observations, negative 1, so we will divide negative 1550 by 4 to get the covariance. We divide this by 4 to get the covariance. So here the covariance is negative 387.5. We can only benefit from the negative sign, that we know there is a negative relationship between the salary and the number of years. But how strong this relationship? Is it near to 0.5? Is it near to negative 1? To know this, we need to standardize the covariance, and the standardized measure of the covariance, as we said, is the correlation coefficient. So to calculate the correlation coefficient, it's simply the summation of the difference between xi negative x bar multiplied by yi negative y bar, and we divide this value by the square root of the summation of the difference square for x's and the difference squared for the y from their mean. So this is why we needed to calculate xi negative x bar squared. We just square the value here. So here, to get the 22,500, we have to square the 450, and here we square the 50. Here we square the negative 500, and here we square 550 squared. For the y's, we have to square the difference between yi and y bar. So here For the correlation, it's the same as the covariance. The numerator is the same, but the denominator is divided by summation of xi negative x bar square, and here the square root of the summation of yi negative y bar square. So here we find the sum, which is 880,000, and here the sum of the difference between yi and y bar square is 14. So we just put this number, which is the here negative 1550 divided by the square root of the summation of the difference between xi and x bar squared, and here multiplied by 14. After calculating this amount, we find that the correlation coefficient is negative 0.44. So there is a negative weak correlation. It's a negative correlation, but it's weak. It's not so strong as if it's strong, we say it's above 0.5 if the correlation is strong. So here we say there is a weak negative correlation. There is a correlation, it's negative. It doesn't imply that if the years of experience are increased, the salary will be increased too. There is a negative correlation. Sometimes people with less number of years of experience get higher salary. This may be referred to the level of education or other considerations put while setting the salary of each employee. I hope you get all these concepts, and thank you for watching the video.